Okay, so I guess I'll try to talk about slotted pages and log structured storage. So we actually had a really big talk about slotted pages in general and about logs and about I think it was called index-oriented storage or something like that. So this is essentially where you have like your B plus tree, and inside of the B plus tree, you sort of just keep your tuples in there, right? So that's what like index-oriented storage was. Right, so you have both slotted pages and log structured storage. We talked a whole lot about slotted pages, but we did not talk about log structured. Now, first, let's try to like sort of answer these. So I guess I watched like this lecture over here. I haven't watched lecture 6 yet, but it's okay. Like we're really close and we're really like on the right track here, right? So which of the following statements are true for database systems using log structured storage, right? So let me just like copy this here. There you go. Right. So using log structure storage. Now, what this course primarily means by log structure storage is some sort of way of actually sort of like, okay, we're gonna imagine a data structure where we pretty much have we can do, so our main API is gonna be a puts call, right? So okay, what we're trying to do here is, if you remember the slotted pages from last time, you remember that you had sort of a record ID. So each tuple essentially had a record ID, right? There you go. Right, so each tuple had a record ID. Now, if you remember, using this record ID, you could actually uniquely identify a tuple. The record ID was made out of the slot number and out of the page number of the actual tuple. Now, you should watch the previous video in order to like sort of understand what a record ID was. Now, in a put call in log structure storage, we're just gonna have sort of kind of a record ID here. So this is like the ID of the tuple, I guess, but this time the record ID is more general. So I think I'll actually avoid calling it a record ID, and I'll just call it like key, for example, 101. This is exactly how they did it in the course. And we're going to be calling it that because it's a whole lot more general, in the sense that you don't have actual pages anymore or slots. So what you have is just some sort of like abstract key, which is presumably a number. It's probably just a monotonically increasing number or something like that. And then on the right, what you get is the actual representation of a tuple, right? So this is the actual like sort of value, I guess. And if you want to remember how representation of tuples was done, you can actually watch the previous video again. But in essence, a tuple was just sort of just bytes on disk that we store somewhere. Now, the way we're gonna do this in log structure storage is we're gonna have something which we're gonna call a mem table. Now, a mem table can be a B plus tree or a binary search tree or some sort of like structure that kind of like keeps its data sorted, or there's an easy way to get its data sorted. So let's try to reason about it while thinking it's a binary search tree, right? So we're gonna assume it's a binary search tree for clarity, but it doesn't have to be that. Right, so the way this works is you have okay, let's say you do something like you do a put on okay, a particular key. Right, let's say those are sort of, I guess, numbers. and we're gonna use v2, v1 for the actual value, right? So you do puts of that, you do v2 like that, then you do of 21, like your v3 here, right? So the way this actually looks is you only have this put operation. So you could imagine here our mem table, which is actually going to be a binary search tree. So you're going to have like your 32 node here, right? And then your 37 node, say on the right. And then your 21 node, say here on the left. And then let's say you insert another node like, I don't know, let's say you do something between those two. So you insert, I don't know, 28, I guess, with v4. So you drop another one here and it's 28. Now you could imagine, let's say you drop another one here and it's like 17. Now you could imagine that this is actually you writing to the database, right? So there's like some sort of, I don't know, application, or maybe this is part of a database management system and somebody is just trying to like ram writes, right? So you get like a lot of writes. Now you can see that the writes are essentially extremely fast due to the fact that you're just modifying a binary search tree or a B+ tree. Essentially you're just going through memory, and because you're using memory, you're much faster than actually trying to like go through a buffer pool manager, pull memory in with a slotted page, identify the record ID, and so on, right? So you don't want to do that. You want to do this. This over here is much more efficient, right? So what happens is that you have a particular threshold on memory because you don't have sufficient memory. So let's say, I don't know, you have like X kilobytes, or they say in the course it's like a few hundreds of megabytes, you know, something like that, right? It's similar to that. Anyways, once you hit this particular threshold on actual memory, what you do is you actually start you compress this into an SS table, right? So essentially you could think that there is like a one-to-one mapping between your mem table over here and your SS table. So your SS table is essentially just these values sort of in sorted order, right? So I guess you know, something like, okay, well, 37 has v2, and then 32 has v1, and then 21 has v3. No, I guess this is 28 has v4, and then 21 has v3, and then 17, which I didn't place here, right? Say that's like v5. Okay, right? So you compact this into what we call an SS table. So an SS table is pretty much just the representation of this as a sort of a sorted list, and its main important factor is that it's on disk, right? So it's a sorted list that lives on disk. All right. So another important feature of it is the fact that it's immutable, right? So you usually do this in levels, right? So you have something like level 0 here. So now you could imagine that once you hit the threshold, you drop this mem table, you compress it, you make it into an SS table, you write it to disk, and then what's actually going to go on right after you write it to disk, I guess your mem table will actually become empty, right? So you delete your current mem table, it becomes empty like that, and then you can do writes again inside of the so you can act upon new writes, right? So you could imagine, okay, let's say this one fills up again. What do? Is I actually take my SS table over here, right? I make it into another SS table like that, and I sort of yeah, so I drop it again, right? And I sort of have to keep them ordered. So I know, like, okay, this is the most recent one, and this is the least recent one, right? So this one's gonna, of course, have different values, so don't get confused here. And you can actually have the same value twice, and you can resolve these conflicts based on recency, right? So if you get another 37 here and you have a value of v7, which is, say, presumably another tuple, you know that this is more recent than this one. Now try to think of deletes. We only have two operations on memtables, which is put and delete. Now delete, essentially what it does, you could think of delete as being equivalent to a put 32 to something like a -1, right? This -1 over here is called tombstone value. So this tombstone value just sort of represents, right? This tombstone value just sort of represents, okay, well, it's pretty much, okay, we just placed -1, which means it's deleted, right? So this is actually equivalent to this. So you can think of, okay, if 31 is actually not in the mem table, it's not in the binary search tree, then you actually create it and you put the tombstone value here, such that when you actually write the SS table to disk, what's going on is that this over here sort of gets, okay, well, we're going to place 32 and we're going to map that to -1, right? So that's quite important. We're going to take the 32 and we're going to map it to -1. There you go. Right, so now you know if someone's searching for 32, you actually know it's deleted. Now, I won't go into optimizations or other things like that, but I'll also mention one thing, which is called compaction. Compaction pretty much means, as you can think, compacting two different SS tables. So let's say you have sort of multiple things here, right? So that's not 31, v2, 34, v7, right? What's going on here is that you can actually merge these two together. Now, how do you merge them? You can actually think intuitively, if you've done an algorithms class, how would you merge those? I won't go into details, just take two pointers and figure it out by yourself. I hope you can do that. But anyways, essentially here at the end we're going to be keeping 32 -1, but you can see that we wrote 32 here, we wrote 32 again, and now when we're going to be merging, we're going to be writing 32 in this new bigger SS table once more, right? So we sort of write the SS table multiple times. All right. Which is quite important. This is called write amplification, right? The fact that you sort of write the SS table again and again. Now, why do you do this? You do it because compared to like the original slotted page that we talked about before, you go much faster if you go this way. Essentially, engines like Cassandra use this, where you're interested in having very fast write throughput. Right, it's much more interesting to do it this way. It's much faster to do it this way. Okay, and they also talk about the fact that you sort of have sequential I/O. Now, I'm not sure about that. You can maybe argue with it. I don't know enough, I guess, about file systems to be able to say whether that's true or not, but yeah, I mean, the fact that professional systems are using this says all that you need to say, because if there's money in it, then it's actually useful. Okay, so using log structure storage, right? So it does cause write amplification, that's true. No, it doesn't. Log structure storage requires the database management system to check previous records and update operations. It doesn't, because actually update operations, you just do update operations in memory. So update operations are essentially the same. So saying this was 32, let's say it was mapped to v1. By the way, we're keeping key value here, of course. Now, if someone comes in and does a put on 39 with on 32, excuse me, with v9, we'll just swap this with v9, right? We don't care. We just write it to memory. And there's also probably a write ahead log where we actually, like, before modifying our data structure, we're going to say, okay, we're going to modify it to this or to that or so on. We don't care about that. Okay. All right, so this isn't true. Can cause fragmentation. I'm not sure about that. I'm not sure what they mean by cause fragmentation. Fragmentation of what exactly? Yeah, I'm not sure what they mean by this. In leveled compaction, SSTables within a level are non-overlapping on key ranges. I think this is false. Right? Because on the same level, within a level, except level 0 are non-overlapping on key ranges. I don't think that's necessary. So you sort of like merge these two, right? So you sort of like merge these two, you get 31 here, and let's say like then you delete these two, you take them out, but let's say the exact same thing happens again, and then you merge and you get 32 negative 1 here again, right? So if there's the same key twice, then that means essentially they're overlapping on the same. So I think this is false as well. Now I'm not sure about what fragmentation means. So I guess this is false. I guess this is false. Can cause fragmentation. Yeah, I'm not sure. Hey, let's go to the next one. Okay, so this is definitely false. Yeah, this is also extremely false because, for example, whenever you update a tuple, you may not find enough storage in that particular slot. So if you don't find enough storage in that particular slot to like sort of modify it in place, what you're going to end up doing is essentially creating a new record ID and moving that tuple around. So this is just false. Slot page storage can increase random reads and writes. This is true because sort of like imagine that if the tuples, if you have like heap file organization, right, and the tuples are like sort of like random in memory and these sorts of things, then you're gonna actually end up with bouncing around pages a lot. So if you like take a page from a certain like sector of a file and then you jump around and you take another tuple from there, you're gonna have a lot of random reads and writes. This is false. This is definitely false. As we actually talked about how we keep variable length tuples. It's actually not a problem at all for us to keep those. So I guess it's only this one. Okay. I mean, it depends, right? I mean, sometimes slotted pages do update tuples in place. Sometimes it doesn't. So I guess this is false. For an append-only workload, both achieve comparable performance, right? That's extremely false because, right, that's just false. LSM trees, right? So yeah, this is log structured storage, and these are called LSM trees, right? Log structured merge trees, and that's what we call these. Okay, slotted page requires storing schema metadata with the tuple, while log storage does not. No, this is also false. I mean, you can store the schema metadata wherever you want. You don't have to store it with the tuple. And log storage also just doesn't necessarily have that. You can store it somewhere else in the system catalog probably. For an append-only workload, both achieve, right? Both designs require background. This is also false. Log structure storage may actually take a whole lot more disk space because you may like end up with the same value twice before you do compaction. So both designs may require background maintenance to reclaim space after numerous inserts, updates, deletes. I think this is only applicable to LSM trees, so I'll go with none of the above are true, right? Okay, so let's see if I'm right on any of these. Log storage does not require that they check previous log records on updates. Level compaction has non-overlapping key ranges for SSTables on each level below the 0th level. I'm not sure how that works, actually. I'm really unsure of how that works. And so what is this? In level compaction, SSTables within a level are non-overlapping on key ranges. Yeah, I'm not sure that's actually true. Yeah, we'll leave it at that. I don't know. Yeah, I wasn't thinking of this. I was thinking of like something else, but I guess I got the wrong answer. Okay, so I got this wrong as well. Amazing. Absolutely amazing. I have no idea how this works. Like like, I don't know. I was right on this. Yeah. I mean, it may benefit, right? Because you may like end up with empty things, I guess. Okay, yeah, that's it. I did my best explanation of SSTables. I mean, they sort of like stay theoretical to me, and I just like know sort of like the main things, but I can't comprehend more without like having to go on extremely deep into them. But I guess it's okay.